Hey guys, today we're going to take a look at the intersection of two lines. Now, before we begin, it is worth noting that even though this is called 9.2 in your notes, it is 9.1 in the text. Okay, which we did already do some of 9.1 in the text, but so this sort of finishes it off. Anyway, so there are four possibilities when we're looking at the intersection of two lines in three dimensions. And so the first one is sort of the obvious one here. And this is when they are intersecting. So intersecting. Okay. And that's just sort of what, that's the normal obvious one. Okay. The next one is when they are parallel. And coincident. So in other words, this one, that's a fancy way of saying it. Essentially, it's the same line. It's not because you give two equations. It's not considered the same line, but it is. It's just these two lines are taking place in the same space, and so they have an infinite number of points of intersection. Okay, so next we can have some parallel and distinct lines. Parallel and distinct. And it is important that you say distinct because, of course, if they're parallel and coincident, then it looks different. Okay? And finally, we can have what is called skew. The two lines are skew from each other. And this means that they're not parallel. Okay, so not parallel, and they are not intersecting. Okay, and so that's all the possibilities. I ran out of room there. That's fine. Okay, so that's all the possibilities for two lines in three dimensions. So, how to find the intersection between two lines? So, the point of intersection between two lines, L1 and L2, and we're using vector equations here, you'll notice, is given by the solution of the following system of equations. Okay, so the system of equations is going to be x01, hold on, let me zoom in so that this is legible, x01 plus t times u x1 is equal to x02 plus sux2. And then we just, same thing for the y. That's a t. Equals y02 plus SUY2 and Z. People always ask me why I cross my Z's. This is why. You'll notice my 2's look like Z's. But because I cross my Z's, whoops. Oh no, that's right. You can tell the difference. So 02 plus SUZ2. There we go. Okay. So this, so we find the solution to this system of equations, which will not always exist, and this will this will tell us. Okay, so I'm going to refer to this system of equations as star. Okay. So let's take a look at the different options. So the first one is a unique solution. So this was that first one we looked at, where there's just two lines and they're intersecting. Okay. So if by solving the system, which is the one we called star, you end by getting a unique value. Oops. Oh, I put the word value twice. Didn't need that. All right. A unique value for T and S. Hold on. Okay. satisfying the system, then the lines have a unique point of intersection. Oh, and that's still my eraser. Unique point of intersection. There we go. Okay. So to get this point, we substitute either t value into line L1 or substitute the s value into L2. You should get the same answer, of course, because that's the whole point, is that this is the point that lies on both lines. Okay. So we're going to take a look at this example here. So first of all, okay, so the first thing we're going to do is we're going to write these as parametric equations. Well, no, we're not. We're going to do this guy right here. So you're kind of breaking it down. So what this is, if we go back up to here, you'll notice this is the parametric equations for the first line, and then this is the parametric equations for the second line. So that's what we're going to do, okay? So we're going to break it up like that, okay? So if we look at the first one, we get t, okay? So the x-coordinates for line 1 is t, and then the second one, it's -3, okay? Our second one will have 1 minus t, okay? And then the y for the second is 4 plus s, okay? And then for the z's on line 1, we get 2 plus 2t, and then we get -4 plus 2s. Okay, so I guess if you're having troubles coming up with this part, you can actually write out the parametric equations first. But again, this is the parametric equations for line 1. This is the parametric equations for line 2. And we've just let the x's equal each other, the y's equal each other, and the z's equal each other, which makes sense because that's what we're trying to do. Okay? So this one actually works out fairly simply because that very first one we have that t equals -3. Okay, so if we call this equation 1, this equation 2, this equation 3, so for this one, okay, we're just going to whoops, that's a t. Sub equation 1 into equation 2. Okay, so we have 1 minus, and then we had that t equals -3. Okay, and then we get 4 plus s. And of course, if we hadn't had it already where the t was isolated, you just start by isolating that t. Okay, but from that, so we get 4 equals 4 plus s. So we get, go up here, that s equals 0. Okay? So there we go. So we found s, we found t. So the question is, does it work? So what we have to do here now is plug, plug t and s into the third equation. Okay? So by doing that, we're just going to be, checking and making sure that it does in fact work. So we'll have 2 plus 2 times -3. Okay? So we'll do, technically, this is one where people will do this the wrong form. This is a case where you should use left side, right side. Whatever, you'll see. Anyway, so 2 minus 6, so that gives us -4. Okay? So then we do the right side. Okay? And for the right side, we had, where is it? -4. -4. I lost it. Plus 2 times 0, which equals -4. So we're good. So it is a unique solution. Okay? So this gives us a unique solution. All right, so now we have to figure out what that unique solution is. And again, you can use either of the equations. It doesn't make a difference. So because the S was 0, I'm just going to use L2. Okay, so sorry, hold on, before I do that, let's write sub S equals 0 into L2. And again, you could have subbed the t equals -3 into L1. It doesn't make a difference, but because S equals 0, I think this is going to be easier. Well, I know it's going to be easier. So we're going to get -3 for -4 plus 0 times 0, 1, 2. And of course, because this is 0, that just disappears. And we're left with -3 for -4. Okay? So, therefore, that point is equal to the intersection of L1 and L2. Okay? And there we go. Okay? So the next case we're going to look at is when there's an infinite number of solutions. So, if by solving this system you end by getting 2 true statements, so for instance, like 2 equals 2, okay, that's obviously true. And one equation in S and T, then there exists an infinite number of solutions. Okay. So, therefore, the lines intersect into an infinite number of points. So, in other words, they are parallel and coincident. Okay. Okay, so there we go. So let's look at how this works. So again, we do start the same way. You're going to break down the first one into parametric and then the second one into parametric, and you just let the x's, the y's, and the z's equal each other. So for the first one, we get t times 0, so that's just going to be 0. Okay, and then on the second one, we get 0 plus 0, so it's still just 0. Okay, so that was our x, which you'll notice that's true. 0 does equal 0. So the second one will have negative t is equal to -6 plus 3s. And we will get 2t is equal to 12 minus 6s. So this is our system of equations. And right off the bat, we'll see that this is true. Okay? If it was false, well, we'd have a problem, okay? Well, we wouldn't really. We just know it meant it was not this. It would be one of the other ones. Okay, so what we're going to do is we're going to, well, first of all, I'm going to label these as 1, 2, and 3. Okay? So equation 2, I am going to rewrite equation 2 as t equals 6 minus 3s. You'll see I just divided everything by -1, okay, but it is the same statement. And now I'm going to sub 2 into 3. Okay, so I will get 2 times 6 minus 3s is equal to 12 minus 6s. Okay. So we get 12 minus 6s equals 12 minus 6s. In other words, 0, you could subtract everything from everything that works to 0 equals 0, which is also true. Okay. So there we go. So for any value of s, there exists a value of t. So in other words, this is when you get to this point, this is what tells us that they intersect at an infinite number of points. Okay, so therefore, the lines, and again, the way we say it is they are parallel and coincident. Okay, so there we go. So let's jump over to the next one. Okay, so our next one, our third case here is that there are no solutions and they are parallel lines. Okay? So, sorry, I'm just looking for my answer sheet here. Nope, I know I can't find it. All right, so if by solving the system you get at least one false statement, okay, so this would be something like if I have 0 equals 1. Well, 0 does not equal 1. That is false. Okay, then the system has no solution. Okay, therefore the lines have no point of intersection. Whoops. No point of intersection. Okay. If in addition the lines are parallel, okay, which of course would mean that the cross product of their direction vectors was equal to 0, or the 0 vector, okay, then the lines are parallel and distinct. Okay. So, to begin with, we start again. We do the x, the y, the z parametric equations, and we make them equal to each other. Okay? So what we'll have is we'll have negative 2 plus t is equal to, let's see, negative 2s. Okay? And then we'll have 3 minus 2t is equal to, let me zoom in here, is equal to 2 plus 4s. Okay, and finally 1 plus t is equal to 1 minus 2s. Okay, so that is our system of equations. Okay, so I am going to again label this as 1, this is 2, this is 3. Okay, so to begin with, I'm going to isolate t, which actually I can do a sort of a proper notation here. When you take a statement and you just rearrange it, you can just put this equal arrow thing. It's a way to do it so that you can write equations side by side rather than underneath each other. So anyway, we can go t equals 2 minus 2s. Okay, and so then we will put 1 into 2. Okay, which will give us 3 minus 2 times 2 minus 2s is equal to 2 plus 4s. Okay? So if we manipulate that, if we expand that, collect like terms, we'll get, whoops, you won't get that. You'll get 4 plus 4s is equal to 2 plus 4s. 3 minus 4 is negative 1, plus 4s equals 2 plus 4s. You can see these 4s's, we can just subtract them from both sides so they cancel out, and we're just left with negative 1 equals 2, which you may notice negative 1 does not equal 2, so that is false. Okay? So because it's false, right off the bat now, we know that they don't intersect. So the only thing left is to determine if they are parallel. Okay? So to do that, we just take the direction vectors. So we take, let's see, what is it? We've got 1, -2, and 1. You can see why I split this lesson up into 2 days. It's taking forever. This is one of the longest videos I've done. -2, we still got a question to go. 4 and -2. So these are our two direction vectors. Okay? We're going to do the cross product. Okay? You actually don't even actually have to do the cross product here. But I'm going to, because I like doing the cross product. So I'll get -2, 1, 1, -2, 4, -2, -2, 4. When you line them up like this, you can see that they're actually collinear pretty easily, but whatever. Okay. And we will get, so we will get then, so -2 times -2 is +4 minus 1 times 4, so it's 0. Okay, and then the next one's 0, and the next one's 0. And what do you know? Therefore, the lines are parallel and distinct. Okay, so in other words, they're parallel lines, but they're different parallel lines, so they do not cross. Okay. All right, last one. Here we go, skew line. So this one, we're going to do it the same way as the last one. We're just going to get different results, okay? So if by solving the system you get at least one false statement, okay, which again means something along the lines of like 0 equals 1, which 0 does not equal 1, then the system has no solution. Okay? Therefore, the lines have no point of intersection. No point of intersection. Okay? If, in addition, the lines are not parallel, then the cross product does not equal 0. Okay? It doesn't matter what it does equal, it just matters that it does not equal 0. Then the lines are what we call skew. Okay? So there we go. So let's do this one here. And you'll notice that I'm, because this is taking so long, I did come up with equations that are rather easy to come up with. Our system of equations here and tell what's going on. So our first one, we would have 1 equals -2. Then we have -1 equals 1. And then we have t equals 0. And right off the bat, you will notice that's not true. And that's not true. So right away, we know there is no point of intersection. So there is no solution, we'll say. Solution. Because I don't want to write all the point of intersection. It's taking long enough as it is. So the last thing that we're going to do then is we are going to say, well, what is the cross product of these vectors? So in actual fact, I've chosen, what do you call them? They're unit vectors. Okay, vectors we're familiar with. That's actually, that'd be k. And then this one here is I. But, whoops. Regardless, if I do the cross product, I'm going to get 0, 1, 0, which is not the 0 vector, So therefore, the lines are skew. There we go. All right. So I've come up with this little flow chart for you. Okay, we got a flow chart so you can look at what the different possibilities here are. So I want you to go through that by yourself, and then I want you to try example number 5. Okay? So until next time, go Sabres.